So I will try to present you some idea about one new way of observing the sky, which is called the weak lensing. And in this talk, I will present this new project, which is called EUCLID, and see how we can try to get some information about what you call dark matter. And then I will discuss about sparsity. So the room is sparse now, so it's really related to what happened here. So sparsity is very useful for different applications. So we will see how we can use sparsity for to solve some inverse problems. And then we'll see also a very recent work, that paper I just accepted now, about the link between weak lensing and compressed sensing. So there are some people from math here, so certainly they knew a little bit about compressed sensing. And you will see that sometimes you have some very non-expected results. Okay, so just to make a brief review about the cosmology. So we have, I think everybody knows here that we believe that most of the energy that we see, that we believe to be true, we cannot see it. Okay, 70% of the energy is something which is called dark energy. 23% is related to dark matter, and only a few percent is related to the light that we see from the universe. Okay, so it's a very strange model, but it happened that this cosmological model that we have, with only a few parameters, can explain almost everything we see. Okay, so we can explain the cosmic microwave background, the light from the early universe. We can explain the expansion of the universe. We can explain the contents in terms of chemical elements of the universe. So we have the strange situation where we have a fantastic model which works perfectly, but we don't know what is the content of the universe. So I will focus my talk on dark matter here. And there are many indications for which we believe that there is dark matter. So the first one started already in the year 1950. When people were, it was tricky first, we realized that if you look at the rotation of stars in a galaxy, in a close-by galaxy, so depending on the distance of the star to the center of the galaxy, we should have this kind of rotation speed curve. Okay, and what we observe, and in all galaxies the same, we observe this kind of curve. And so we explain the difference between what we should have, considering only the mass related to the light of the stars, to what you observe, as an indication of dark matter. So in order to have this kind of curve, we should have much more mass. So dark matter could be a possibility. So the second indication is that it is at a larger scale. Now we go to the cluster of galaxies. And here again, if you look at a cluster of galaxies, if you just believe that the mass is related to the different galaxies, the galaxies should escape. They should not be closed, gravitational linked. So again, to have all these galaxies gravitational linked together, we need some more mass. Okay. So now, if you go, this is some real data. Okay, why doesn't this? Oh, okay. This is some real data of a galaxy survey of galaxies. So each point is a galaxy. So we see all these structures. Okay, galaxies are not randomly distributed in the universe. We see filaments, clusters, and all these structures that we call cosmic web. Okay, and so we do some simulations trying to reproduce these kind of figures. And there are some people who are very expert in doing this kind of simulation. You can take months on the bigger computers in the world, and then you can reproduce something very similar to what we see. Okay, but to get this kind of same features, we need again to have dark matter. Otherwise, you have no time to create the structures. Okay, so whatever the scales of the universe, we need some dark matter to explain what we see. So there are, for I would say almost 20 years, there was a huge effort to try to track down what is this dark matter. So the first idea was maybe dark matter is just related to stars which are not big enough to start a nuclear process, what we call brown stars, brown dwarf. Sorry. So there was a huge number of programs for 10 years during 1990 to 2000, which tried to find these objects, and they find a few of them, but clearly not enough to explain the dark matter. So this first kind of object, they were called macho, have been, it's clearly not dark matter, the reason of dark matter. So there are a lot of effort to try to track down a mass of the neutrino, and they found a mass, but not large enough to explain dark matter. So now people are thinking that maybe it's a new particle which is called WIMP, and they are trying to find out if WIMP could be the origin of the dark matter. Okay, so there are other theories. And at the same time, where in the years 1980, where people were trying to propose dark matter as a model, there was another, Milgram proposed another theory, which is the Mond theory. And this idea was to change the law of the gravity, and then you can explain this kind of curve. Okay, so during the years 2000 also, there are many people who are trying to see if you can changing the gravity, if you can explain everything, also what you see in the universe. And the results were not so good, so at this point there is a kind of disappointment on this modified gravity, but clearly any new project should also investigate this kind of approaches. But what is clear now is that either there are dark matter or you have to change the gravity laws. There is just no other way. Okay. The gravity laws. Okay. Okay, so there is another way to look at the mass, at the dark matter, is to consider a lensing effect. So we know since Einstein that the light can be deflected by the mass. So for instance, this is real data, it's not a simulation. So we see there is a cluster here, and you have all these arclets, which are due to background galaxies, and the light has been completely distorted by the mass. Okay? So this is what you call strong lensing. And what you call now weak lensing is a small effect. Okay, so imagine that you have galaxies which are far away, and you are here, and you are looking at these galaxies, and the light will be a little bit deflected by the mass, which is here. So imagine now that you are observing a regular grid, like that, and there is some dark matter here. Here is what you will observe, and this is completely amplified. So we are observing some effect which are something like 1% of the ellipticity of the galaxies. So weak lensing is this very faint effect. Okay, so how to do that? So you have to observe a huge part of the sky, and you get this kind of images, as you have seen just before. And we can do even better, we can go to space. And this is the EUCLID project, and it has just been accepted last October by ESA, and it will be launched around 2020. Okay, and it will observe a huge part of the sky, 15,000 degrees. Okay, the whole sky is 40,000 degrees, so it's almost half of the sky. And there will be 4 bands, and we will observe more than 1 billion of galaxies. It will be between 1 and 10 billion galaxies, and we will obtain the spectra for 50 million galaxies. So a huge amount of data. Okay. And we believe that it will be something like 850 gigabytes per day to track down. Okay, that's the project. So now how can we do? So the first thing to do is first detecting objects in the image. So detecting stars, galaxies. This we know relatively well how to do that. So we have some tools. The most famous one is called Extractor. It's available on the web, and every project just takes this software, get all the objects, and then there's a kind of classification, so you can separate stars and galaxies. So this is a kind of standard tools in astrophysics. So now we need to define the shape of the galaxies. The shape. So we'll see why afterward. Okay, so we use 2 parameters, but we define the shear, which is a distortion of an ellipse, and we are measuring this kind of information. Okay, and so we are deriving the shear from the measurement. Okay, so the shear is completely related to the second order moment orders of the galaxies. Okay, for one galaxy. So you can measure the shear for each galaxy. But the point is, if you want to have a good accuracy on the cosmological parameters, we need to have very, very accurate measurement of the shape measurement, okay, of the shear. So that's the first problem, how to get a very accurate measurements on a small galaxy, taking into account that you have noise on the data, okay? So why to go to space? I think this image is clear. So if you have one galaxy observed in space, like this one is a Hubble Space Telescope image, a simulation, and this one is the same image which has been distorted by the shear effect, okay, by the mass. So it's a very small effect. But if you go on ground, because of the blurring of the atmosphere, so here's what we get. So you can imagine it's very easy to see that we need to have a high quality image, which we cannot have on ground if you want to have very accurate measurement. Okay, so the second problem is everybody who was working with data know that there is an optical problem, which is the point spread function of the instrument. If you observe a Dirac, a star is like a Dirac, okay, because it's so far away. You don't get a Dirac on your image. You get a kind of something, a kind of Gaussian or something which is spread out. And this function of spread out is called point spread function. And if if the optical of the instrument is not perfect, which is always the case in the real life, so it may not be completely symmetric. So you can consider that the asymmetry that you are observing is due to the galaxy, but in fact it's due to the point spread function, to the optic of the instrument. So you need to correct the ellipticity that you are measuring from the effect of the instrument. Okay, this is very important. So that's the second problem. Third problem. So you see that there's a lot of work to do. Third problem, you have observing a big image. You have one galaxy at a given point, and you have several stars, and each star is a kind of model for the point spread function. But the point spread function is varying spatially because of the optic of the instrument. So it's not stationary. So this one will be slightly different from this one, slightly different from this one, and so on. But now we don't know exactly what is the point spread function at the position of the star. So we need to correct the shape of the galaxies that you are measuring here, knowing the shape of the stars, but at different position. We don't know the shape of the star here. So it's a kind of interpolation of the stars that we need from here. And this is a completely open problem because you want to have a shape measurement, and you want to correct the shape measurement from other shape measurement at other position. Okay, you see how complex it is. It's really not clear what is the best strategy to do this kind of thing. So the last point, which is obviously very important, I told you that the shear due to the dark matter was something like 1% of the ellipticity of the galaxies, of the intrinsic ellipticity of galaxies. So you are measuring ellipticity, but clearly the galaxy has its own ellipticity. So when you are measuring an ellipticity, is it due to the galaxy or due to the dark matter? It's completely not clear how to do that. Okay, so now I will try to give you at least what you can do up to now, and we are clearly hoping that in the next years we will improve everything a lot. Okay, so how to do that, especially for this intrinsic galaxy ellipticity. So what we are doing is now we are dividing the images into blocks. And we want the block to be large enough that inside each block we have at least 30 galaxies. That's a kind of goal that we need. And if there is no dark matter at all, so there is no reason why the galaxies should be oriented in a given direction. The direction of the galaxy should be random. Okay, so if you average the shape of the 30 galaxies, it should be something around 0. There is no reason why there is a privileged directions. But if you have some dark matter, it acts like a gravitational force, then all of them, they will be shear in a given direction. Okay, so if you average the shape parameters, you will have a small bias. And this small bias is related, in fact, to the dark matter. Okay? That's the way that we get rid of the intrinsic ellipticities. So for each galaxy in a block, we need to measure its shape, to correct it from the point spread function, and to average all of them, and then we get 1 point of the shear measurement. Okay? That's the way that we need to do. But we are not at the end of the story, because now we have also to deal with some missing data and some noise. Okay? So we have a kind of triple inverse problem to solve, which is determine the point spread function at any position in the image, determine the shear of each galaxy and to correct it from the point spread function, correct the shear from the intrinsic ellipticities, and then take into account missing data and noise.
Can I ask you a question?
Sure.
Do you make any a priori hypothesis about the distribution of this dark matter?
So here, when you say that you have a big, when you say that you have a block with 30 galaxies and you average the shear, obviously we have a prior here, is that the dark matter is not changing inside the block. Somewhere you have this prior, that the dark matter is something, or doesn't change too quickly. Yeah. Okay, so there is a kind of prior, you are right, yeah. So there is a lot of efforts which have been done for the last 10 years in order to try to compare algorithm. And this is very interesting. What happened in this domain of the astrophysics is they are creating challenges. And they also try to gather other community, and especially the pattern recognition community. And so they made some challenging, and the winner get something like an iPad or something very funny. But at least it works, and there was 5 challenges already organized. And in the last one, we just got the results last September. And so the idea was there was 2 challenges, one with galaxies and the other one with stars. Okay. And then the idea is one data set of simulation where everybody knows the answer, and there is another one where nobody knows the answer. So you can try your algorithm with one data set, but then you give the result for the second one. And that's the way it works. And there are many groups in the world who are participating, and not only groups in astrophysics, also groups in pattern recognition domain. And so there was this kind of galaxies that you need to measure the shear. So you have a bunch of galaxies. Okay. So there was, and for the star challenge, there was something like 40,000 stars. Okay, and so you have an image, and and the goal was to get the position of the star, the shape of the star at each pixel of the image. Okay, so what they had at the end is, you see all these methods which have been developed. It's a lot of them, right? So just to let you know that there is a huge effort in order to get the best we can for this kind of problem. And finally, the group who did the best results was a group who used a parameter modeling of the stars. Okay. Sorry?
Who was the team leader?
This was at the EPFL. It's a group with Frédéric Courbin at EPFL. And so at this point, what is not clear to my point of view is this parametric modeling the right approach, or it is just because the simulation was too simple? That is not clear. Because if the simulation are too simple, clearly a parametric model may be the right approach. But in practice, maybe the simulation were too simplistic, and I think you have to figure out and to work better, to better understand what's happening. Okay, so that's the situation. And for the galaxies, there was something like 10 to the 4 galaxies and 10 to the 3 images, so 1 terabyte to process. So you have seen that each group had to invest a lot of effort to process all this data. And again, there was these challenges with all these methods, and what's interesting is finally the way to get the best results were having a method estimating the shape, and because you know on the simulation what is the true, estimate the bias. with simulation. And then when you get to the other data, you use the bias to correct it. And that's it. And the group who did that also get the best results. Okay, so somewhere there was this kind of approach which is interesting, but this bias is something which is very strong. And if the model that you are using for the simulation doesn't correspond really to the truth, then maybe the bias is not so good to use. I don't know. So at the end, we have this shear measurement, okay? And to get the cosmological parameters, to get some information about the astrophysics, you need to make some statistic measurement on this shear. And one way to do it is to compute the correlation function on the power spectrum, and then from a given cosmological model, you can just have some prediction. So you can compare what you get from the data to the power spectrum. Another thing that you can do, you can reconstruct from these shear maps, you can reconstruct an image of the dark matter. Okay, so you cannot see it, but you can image it. Okay, and there is some relation to do that. Okay, this is a kind of relation between the two. And there is some quite easy equation between the shear and the dark matter mass map. So this is in Fourier space, and you can just invert this equation. So, but if you do that, again, it's very, very noisy, and you have a lot of problem, because what you get is this one. So at this point, we have investigating sparsity to solve the problem. So sparsity, we want to regularize y equal x plus some noise, and you have, so you express your data in a given dictionary, so we call phi. So we said that the data are sparse in phi, and you have this kind of norm to minimize. Okay, and so we want the dictionary which provides the sparseness representation. So we said that we want a dictionary where when you decompose the data on the dictionary phi alpha, so when you sort the coefficient from the larger to the smallest ones, you have the fast decay. So that's the traditional approach in the sparse domain. And what you want generally to minimize is the L0 norm, which counts the number of coefficients. But we know that for a couple of years that you can replace it by the L1 norm, which is the sum of the absolute value. And if the solution is sparse enough, both problems are the same. Okay, so just to give you an idea of how it works, if you have just y equal x plus some noise, so it's a denoising problem, so you solve this problem, and you have this equation to minimize, so you replace x by phi alpha, and to solve it you have this iterative thresholding approach, and the fantastic things and the miracle here is phi is orthogonal. You just have to apply one iteration to get the exact solution of the problem. So we just take the data, decompose in the dictionary, threshold the data, set to 0 some coefficient, and reconstruct, and you get the solution. Okay, so you have the same for the L1 norm, but don't go too further. And if you have an inverse problem, you can just iterate this iterative thresholding, and you get the solution. And so this is very simple algorithm, but for the last 5 years, there is many new algorithms which are much faster and that you can use. Okay, so what is a dictionary in astrophysics, which is generally the best? It's what you call isotropic wavelets, what I call it starlet transform. So it's not orthogonal wavelets, it's frame, and it's isotropic, and it's generally very good for astrophysics because most of the objects are more or less isotropic. So there is no reason to have a three-directional wavelet transform, for instance. Okay, so, and it's a decomposition where each wavelet scale has the same size as the original image. And the reconstruction is completely straightforward because you just add all these 6 images and you reproduce exactly the original image. Okay, so from the physical point of view, it's very easy to understand what's going on through the scales. Okay, so this is kind of denoising results. You have one image plus some noise, and that's the denoising, and that's the residual. So you see that you can really clean up the noisy image and to get some very good results. You see, for instance, here and here, it's very faint objects that are completely in the noise, and you can still recover them. That's another dictionary that you are using sometimes when you have some kind of feature which are directional, is you are using a curved transform, and this is a result of deconvolution using curved transform. This is real data, infrared data. Okay, so coming back to this weak lensing problem, So here is the data, in fact, the shear that you are measuring, and here that you can reconstruct. So in red it was the simulated data, and in white is what you have recovered. So we have seen that even if it was very noisy, we can still recover some information and some clusters. Okay, and if you compare to other techniques, clearly this is the sparse denoising. And if you show the curve, we see that the sparse reconstruction is much more efficient to recover the different clusters. Okay, so now how to deal with missing data. So I told you that you have also this problem. So every time you have a star in the image, you have to mask this part in the final reconstruction. You cannot use it. Okay, so you have to deal with this kind of mask in practice. That's real mask that you have to use with different survey. So this comes back to the thing that you have developed many years ago, which is called Inpainting, is how to fill the gaps. And when I started to do this work with David Donohoe and Mickey Elad, I didn't realize that it could be useful for the weak lensing. It comes only 5 years later, and I see that it was very useful for that. So this kind of inpainting was very similar. You have some missing data, you have a mask which is equal to 1 when you have some information and 0 when you don't have any information. And you can just, using this iterative thresholding algorithm, at each iteration you take the solution, you decompose in the dictionary, you threshold and you reconstruct. And with this simple iterative reconstruction you can do an inpainting. So to give you an idea how it works on images, so here the dictionary was a combination of curvelets and DCT. And there is 20% of missing pixels, and here what we recover. 50% here what we recover, and 80% of missing pixels, and here we can still recover something from the data. So this inpainting is working very well. And that's another example which was quite impressive in astrophysics. These are some temporal data that you observe, and there's a lot of missing parts. And if you look in the free domain, the missing data creates lines at the harmonics exactly at the same position where we are looking for scientific harmonics. So they had a lot of objects which could not be processed just because of that. And there was many data which was sent to the trash just because of this missing data. They've tried everything, and when they process this sparse inpainting, they could show that using simulation that it was really doing a nice job, and they could just recover all the data. So, and this is in 3D, the inpainting in 3D using beam curvelet. Okay, now coming back to the problem, you can rewrite the equation in order to take into account the mask. And now we want to recover the dark matter mass map from the shear, and we know that you have some missing data. So we are going to now to invert this equation, and we want the dark matter to be sparse in a given dictionary. Okay, and it's exactly this problem that we will solve, and we see that now how it works, or here, and here it's what the algorithm is providing. Okay, so people in astrophysics are very reluctant to this kind of approach. It's really not a standard way to process data to fill the gaps. Okay, so we have to convince people. We had to really make a lot of Monte Carlo simulation and to show that if we do this kind of inpainting, we can recover the power spectrum with something which is around 1% of error. So we can not only make nice images, but we can really compute the power spectrum and make science out of the data. There is an error, there is a bias, but you can have an estimation of these errors. And if you go to higher statistics like bispectrum, again we can show that we have some very good results, and the errors is something around 3%. Okay, so inpainting can really be used, but clearly we need some Monte Carlo in order to figure out what is the level of errors. So on real data, so we have applied to this tool on real data, and this was data from the Hubble Space Telescope, and what we see here is in blue is the light from the stars, and in white is what you have reconstructed from weak lensing. And the results and the result was what we see here is there is clearly the same distribution of the dark matter and the visible matter. Okay, so the dark matter is not at different position compared to visible matter. So that was an important result. So another application of sparsity is the discrimination of cosmological models. If you use only second-order statistics, it's very hard, for instance, to differentiate two parameters, which is the quantity of mass and the fluctuation of the mass at a given site of the universe. So with second-order statistics, any cosmological models on this banana cannot be discriminated. So we have done a bunch of simulations, and we have, for each cosmological model, we created many simulated data, and we have looked if we can have a better information using the statistics, for instance, in the wavelet domain or in the curvature domain, and we have tried many things. And what we found out is if you count the number of peaks larger than a given threshold in the wavelet domain, it's a very efficient statistics for the discriminations. So we have seen that we were very able to see that the histogram of the statistics for the 5 models. So they are very separated. Okay, so here we have seen that sparsity and especially wavelets were useful for inpainting, for reconstruction and denoising, and also cosmological model discrimination. And another aspect of Weak lensing is what you call tomographic Weak lensing. So we can separate in a given image galaxies which are at low redshift and high redshift. So redshift is related to the distance of the galaxy to the Earth. So we can separate in two different in 2 bands or more bands, in several bands, and we can compute the power spectrum for different redshift. So doing this tomographic Weak lensing, we can follow the evolution of matter during different periods of the universe. So it gives us a lot of information about dark energy, of these kind of things, because it's related to the way that the universe evolves. Okay, so tomographic Weak lensing is really one of the goals of the EUCLID project. And you can do even better. You can try to reconstruct 3D dark matter, okay, not the projected mass as we did before. So we can do some kind of pseudo lensing. So for each band of redshift, for each part of the universe, you can invert the same equation I have shown before. And then you can reconstruct this kind of maps. But this is not perfect because each part of the universe is not independent of the others. You can imagine that if you have one cluster of dark matter here, it has an impact of all the galaxies which are behind. Okay, so it's a real tomographic problem. You cannot separate by part of the universe. So if you write the equation on one line of sight, you can see it as a 1D problem. On one line of sight, you have this kind of relation where the shear is related to the kappa here, and the density of the universe is here. And you have a matrix which is called the Lensing efficiency matrix. So it's a pure inverse problem, 1D inverse problem. So we can just write this equation, and if you look exactly what it looks like, it looks like that. So here you have the data, you have different redshift bins. Here is the density here, it's in 1D, right? So you have to repeat it for each line of sight. And here you have this matrix which has the effect of spread out the information everywhere. So each cluster here will spread out the information along all these measurements. Okay? So, and you have some noise. So if you look at this equation, some people in the room suddenly recognize something. This is very close to the compressed sensing problem. And in the compressed sensing problem, the only difference is, okay, maybe for a mathematician is a fundamental difference, is the matrix is random here. Okay? So in the compressed sense, in the Weak lensing, the matrix is not random. But it has still a kind of similar effect, which is to spread out the information on all the measurements. Okay? So it has the same kind of diffusions. So we have the same problem of underdetermined problem. Okay, so we have less equation than unknown, so unknown are x. We have a matrix which spreads out the information, and what compressed sensing tells us is that we have to minimize the L1 norm of the solution. Okay, so exactly what we did. So we write the problem as a compressed sensing problem using sparse recovery to get the solution, and we have published this paper now, And what we were able to do is something that nobody could do before on simulation here, is, for instance, to reconstruct 2 clusters along the line of sight. Okay, that's really the kind of thing that we were not able to do before using these sparse recovery techniques. So, conclusion of this talk is that weak lensing is very powerful. It's completely related to the mass and not to the light, so it's completely a different observation compared to previous observations. It's very hard, so you have really to track down all systematics. And for the PSF measurement, for the shear measurement, and for the lensing statistics. We are clearly not at the stage now where we can process Euclid data with the accuracy requirement that we want. We are not, algorithms at this point are just not good enough. Okay, so we have around 9 years now to the launch in order to improve them and to be in the situation where we can fulfill the requirement, scientific requirement. Okay, so the community is very open. So I told you in the challenges that it was already open to the pattern recognition community, and there is a workshop this week at, in the mountains behind Grenada, where there will be these 2 communities together, which will be able to discuss. And finally, this very reason that you have on compressed sensing are very interesting. So we are really pursuing in this direction now, and everything has to be ready for 2020. Okay, thank you.
Okay, there are some questions.
Just a very short comment. What we have been doing in mobile communication is is quite similar. Instead of point spread functions, you are having a slowly varying channel. So while you're moving, there is multipass propagation. There is a convolution kernel, but it changes over time. And from time to time, you receive this pilot tone, so you can identify the channel, and then you try to convert it back to the original position. So I would hope that maybe with that approach in 2D, maybe one can do a little bit in that direction of interpolating the PSFs. I will contact you on that.
Okay.
But I also had a question. I mean, in compressed sensing, the fact of using the L1 norm is something which is quite essential, no?
Mm-hmm.
And then did you reach the same conclusion independently? I mean, from an experimental approach, or I mean, in this weak lensing theory that was developed independently of compressed sensing, and you reached the same conclusions, or how will it happen?
Okay, so I'm really aware about compressed sensing because I knew I was in 2004 just in front. My office was at UCLA in front of Emmanuel Condé, so I knew very well everything about compressed sensing and so on. So when we started to address the problem in 3D from weak lensing, and I saw that at which point the matrix has this effect of spreading out the information, and that you want to solve another determined problem. So sparse recovery was clearly for me the right approach, and also we are really sparse these times because in the direction of the light of sight we are not have enough resolution to resolve clusters. So each cluster is like a Dirac. So we have, it's really the sparse model is completely correct. So we are really in the situation where we are K-sparse exactly. And we have a matrix which spread out the information, and we are underdetermined. So it was making sense for me that the sparse constraint should be the one to be used. So it's called sparse recovery. Then we can, the point is, shall we call it compressed sensing or not? This can be discussed because the matrix is indeed not random.
But at last you are using the same reconstruction.
Oh yeah, yeah. So construction are exactly the same. Yeah, for sure. Yeah.
In the problem of the interpolation of the PSF, could it be possible to have the theoretical PSF like in the space telescope with a latest program or something like that?
I guess we will be able to have some good model. I hope. I don't know at this point. I don't know exactly what we will have. The method which works well at this point, they are modeling the PSF. They use a Moffat shape for and then they interpolate the parameters of the PSF. Is this model good enough for Euclid? I'm not sure at this point. We'll have some discussion next year with people who are redesigning the optics to see exactly if you can have a better modeling of the PSF. But that's a good point. Yeah.
Okay.
You're also investigating dictionary learning for the PSF.
Dictionary?
Dictionary learning.
Ah.
So, you know, so you have many PSF. So there is one approach which is to have a model for the PSF and to interpret the parameters. And another one say, okay, I don't want a model for the PSF. I'm trying to build my own dictionary and I will interpret in this dictionary. Not sure which one is the best, but at least we investigate this approach as well.
To make a point clear, these filaments you are showing, they are filaments of matter that connect different galaxies.
Cluster of galaxies, yeah.
Okay, so yeah, and which is this which kind of matter is this one that connects the two galaxies, for instance? And
No, it's two clusters of galaxies. So
Okay.
so we believe that cluster of galaxies are somewhere related all together by filaments. So it's a kind of it's kind of texture the universe, and what we see is just some points. But if you look at the universe in details, like the first image I showed the movie, it's real data. It's not a simulation. So you clearly see that's true galaxies. So you clearly see that the galaxies are along filaments.
And about the pattern, do the two galaxies that are connected by one of these filaments, do they have the same shear? They share. There is some relation because of that, because the gravity. The two of them have some relation in shears, for instance, or no?
No. So here the size is huge when you look at this volume. So if you have two. Because here the difference, the distance between two galaxies are so large that it's not the same. Yeah.
Have an effect to have the same shear.
I don't know why you asked just this, because it looked like a brain with neurons.
Yes.
Yeah, that's a very good point. You know that in Paris there is one colleague of mine is doing a kind of spectacle with a spectacle entertainment with a neurobiologist, and they are showing simulations, cosmological simulation and brain, neural network in the brain, and they show the similarities and at different points.
This is why I was asking this, because in fact this is because of the isotropy that you were mentioning in the brain. These connections make the two galaxies, let's say, the two pools of neurons, to have the same orientation preference. So this gives an isotropy that makes the pattern a little bit different.
No, but the point is the dark matter is between you and the galaxies.
Yeah,
So yeah. So
The universe is a brain.
Okay.
Thank the speaker again.